Welcome everybody, I am Andrea Puglisi. I am a researcher at the Institute for Complex Systems at the National Research Council in Rome, in Italy. I'm going to present you a brief summary of recent work done in collaboration with Claudio Maggi and Umberto Marini Bettolo Marconi, both working in Italy, one at the University Sapienza and the other at the University of Camerino. This work concerns entropy production in systems of active particles. Active particles can model many different kinds of natural or artificial systems. For instance, at the microscopic scale, you can find birds or fishes, so animals which together display very interesting and quite rich complex collective behaviors, and similar systems can be found also at the microscopic scale, for instance bacteria or sperms, or even at smaller scales like filaments of actin in the cell. These kind of models are typical models of non-equilibrium statistical mechanics. Also for this reason it is important to try to extend the concept of usual thermodynamics to such kind of models, and so, for instance, extending the concept of entropy production. Let's start from recalling the usual basic relations in macroscopic thermodynamics. Usually, during a thermodynamic transformation in a macroscopic system, you have some heat which is exchanged with the thermostat, which is delta Q, and then if the transformation is quasi-static, you have that the variation of the entropy of the system is exactly equal to the variation of heat divided by the temperature. Otherwise, if the transformation is faster than quasi-static, you have some entropy production, which is defined exactly as the difference between the two, and the second principle basically states that this entropy production is greater or equal than zero. So as a consequence of the second principle, you have the closest relation, which basically says that during a cyclical transformation, this integral of the heat exchange divided by the temperature at each instant is less or equal than zero. This is what happens in macroscopic system. The aim of stochastic thermodynamics is to try to extrapolate these basic relations from macroscopic system to mesoscopic systems, so smaller systems where you have fluctuations. So basically you have systems which are described by stochastic models, and every trajectory, every instance of transformation of your system is described by a trajectory, for instance omega of time, which evolves from some initial time to the final time. This is a stochastic trajectory, and the stochastic thermodynamics recipe basically tells you to take the logarithm of the ratio of the probabilities of observing a trajectory and the probability of observing the time reverse of the trajectory. The time reverse of the trajectory is just the same trajectory but in inverse time order, and eventually changing sign to the velocities, to the odd variables. Then you can show that this logarithm of this ratio of the probabilities can be split in two parts, and everything in this identity can be rephrased as integrals of some rate. So the left-hand side is the integral of the entropy production rate, and the first part of the right-hand side is the integral of the instantaneous variation of the entropy of the system. The last part is the integral of the instantaneous entropy production rate, which goes into the medium, into the surrounding medium. In many systems, in many simple models, it can be shown that this part, the delta S m, is exactly equal to the ratio between the heat exchange with the thermostat and the temperature of the thermostat, with a minus sign. So basically, when you do an ensemble average of all the trajectories, you recover stochastic thermodynamics, macroscopic thermodynamics, since you get by probabilistic considerations and basically the fluctuation relation that the left-hand side has an average which is always larger or equal to 0, and the average of the first part of the right-hand side is the variation of the entropy of the system, and the last part is exactly the variation of the heat divided by the temperature, and this is smaller or equal than 0. For instance, the typical simple example which is given to have a flavor of how stochastic thermodynamics works is to consider a colloidal particle in a fluid, in a liquid, for instance. So it obeys these simplified equations, for instance, for one component of its position in its velocity, and the second equation is just the dynamics of the velocity, which contains the first two terms, which are the terms relative to the exchange of energy with the bath. The third term is the external potential, and the last term is some non-conservative force which puts the systems out of equilibrium. And you can define the work as the power, as the integral of the power of the non-conservative force. And then the heat is what remains in a variation of total energy if the work is subtracted, and this can be shown to be equal to the Stratonovich product of basically of the velocity times the force of the heat bath. And so if you repeat the previous recipe for stochastic thermodynamics and calculate the total entropy production rate, you discover that it can be split in the two parts exactly as predicted before, where you have the instantaneous variation of entropy of the system minus exactly the ratio between the heat transfer to the thermostat divided by the temperature of the thermostat. So now our objective, our aim is to try to apply stochastic thermodynamics to a different kind of systems, which are active particles. As mentioned before, active particles are systems of particles which have self-propulsion, and typical examples are bacteria in a fluid, or, for instance, swarming animals, animals with some collective behaviors, for instance, birds in this video on the right. On the left, you can see bacteria moving and actuating basically a microscopic engine, which is made of a rotating wheel. Okay, they basically act exactly as a sort of Brownian motor. There are many different models which describe the basic properties, reproduce the basic properties of separable particles. For swimmers, like bacteria, for instance, a good model which has been recognized in the last years, quite recently, is this one, where the position and the velocity of the particles obey these two equations, which somehow are similar to the equation for colloidal particles, but where basically the non-conservative force is the self-propulsion force, which is denoted by Fa, like active force. And basically the active force is modeled as an Austen-Uhlenbeck noise. Basically the idea is that this force is acting with some persistency along some direction, and then it changes, exactly as it happens, for instance, in the so-called run-tumble model, which grasp quite appropriately the E. coli bacteria and something else. So you have that this force is characterized by some persistency time tau and by some active temperature Ta, or a diffusive coefficient dA. And you can also take the overdamped limit of this model by neglecting inertia. In this expression, you still have the presence of the thermal noise together with the active force and the external potential phi. Then if you apply stochastic thermodynamics to this model, which contains also the thermostat explicitly, you can repeat exactly the same recipe. You can denote by delta W the work done by the active force, and you remain with some heat, which is exactly the heat exchange with the bath, exactly in the same way as before. You can calculate the entropy production. You recover exactly the original result of the general result of stochastic thermodynamics, and so you get an idea of the clauses relation as before. Now, the idea is exactly that this kind of relation is difficult to be verified in experiments, because it's basically impossible to do calorimetric experiments where the heat released from some bacteria to the solvent, to surrounding fluid, because of only the activity of self-propulsion is difficult to be measured. So the idea is to go beyond and neglect thermal noise in the description of the self-propelled particle, based on the fact that the active force is usually much bigger than the thermal forces. So if you neglect the noise in the previous model, you get these simplified models. Now these models can be cast into something interesting because of the particular character of the active force. The active force is an Uhlenbeck process, so it's a color noise. It can be derived, it can be time derived. And so if you do the time derivative of this equation, you get this second order equation, where basically you can see that you can describe the system by considering an effective velocity, which is not, of course, the instantaneous velocity, because it starts from the overdamped description, so it's on a longer time scale. And U, this effective velocity, obeys a sort of Cramer's equation with some contact with the heat bath, an external potential, and something else. And you can collect the last term with the first term in order to get an effective local viscosity and an effective temperature. So you basically have an effective mass mu, an effective viscosity capital gamma, which contains the persistency time tau and the external potential, and the second derivative of the external potential, and an effective temperature, which is related to the original active temperature divided by the effective viscosity. Now, recognizing that you have basically a sort of local equilibrium for this new model, local equilibrium with a particular temperature and a particular viscosity, you can hope that the stochastic thermodynamic recipe can give here some interesting result. And in fact, if you repeat the recipe by taking the logarithm of the ratio of the probabilities of the trajectory and the time reversal of the trajectory, you get again a very similar result for the total entropy production, split in two terms, and the term related to the entropy production in the medium is the ratio between a heat exchange and the local temperature, where the heat is exactly the power of the force, of the thermal force as defined before, which is this thermal force of this effective thermostat. And so basically you recover exactly the Clausius relation for this particular ratio between this effective heat, this active heat, and the active temperature. And you can also understand by doing some more manipulation that this quantity, this average of the ratio in the steady state between the heat and the temperature, can be also computed and measured as a spatial integral of some density or some heat exchange density Q tilde, where this Q tilde is proportional to the difference between a local effective temperature and the local kinetic temperature, exactly the second moment of the local velocity. And so this gives also the idea basically that the system is at some kinetic temperature which is locally different from the effective temperature, and this different excites an exchange of heat, and this exchange of heat is the reason why there is some entropy production at this macroscopic level. So, for instance, if you consider here an external potential which is quartic, you here on the first graph on the left top frame, you see the probability distribution of the position and of the velocity. You see that there is some asymmetry because the system is out of equilibrium. And then you can see on the right top graph the curves which describe the local density for two different choices of tau, and also the external potential, which in the graph is called W, but it is exactly equal to phi. And then in the bottom left graph, you have for two different cases the kinetic temperature compared with the effective temperature. You see that there are regions where one is larger than the other, and region where this relation is opposite. And so in some region there is an exchange of heat in direction from the system to outside, and some region there is the opposite direction. And so if you consider just the density of the heat in the last graph, the solid curve, you see that its integral is zero. You can do this calculation, it's zero, because in this case there is no work, and so the heat in the steady state is zero on average. But if you consider the average of the ratio between the heat and the temperature, which is the dashed line, you see that the integral, the gray part, is smaller than zero. And you can also extend, extrapolate, and generalize this recipe to more than one dimension. In this case, the equation for U is a vectorial equation, a system of equation, and the viscosity, the effective viscosity, is a tensor. But this tensor is symmetric, so you can diagonalize it, and D is the diagonalized of this with lambda, the eigenvalues. And then you can calculate again the entropy production and get a very similar relation, where now you have a vector of heat exchanges and a vector of temperature. But this gives exactly the same result as before. So thank you for your attention.